Hello, this is Charles Sanderson doing another Aspen Custom Modeler ACM demonstration video. A few of you have left comments and likes. Thank you very much for that. It's always great to get feedback. If there's any topics you're interested in, please let me know. Today what I thought I'd do is run through some of the coding tricks and tips that I've picked up over the years. A lot of it's newbie stuff, so this may be, if you're new to ACM, a useful video. If you're an experienced user, it may be one you want to skip. What I'm going to look at is a very simple mixer model and a couple of the different ways in which that can be coded and ways to make it more robust. So first off, I'm going to create a very simple modeling framework. First, I'm going to define a port where I'm just going to say this is my flow, a mass flow rate, and a mass fraction, and that's it. I'm not going to worry about enthalpy or pressure or temperature or any of that good stuff. I'm just going to do a very simple mass balance in this case. Next up, I'm going to define a stream. And initially what I'm going to do is I'm going to say my inlet port is going to use, my inlet is going to use that port that I've just defined, and it's going to be an input. My out main port is going to be an output port, again using my port. And very simply I'm going to say the flow out is equal to the flow in, and the mass fraction out is equal to the mass fraction in. This is an implied array, so Z is, because I defined it in the port as an array dimensioned on component list. This is actually n variables where n is the size of component list. So this is an array calculation, a vector if you like, rather than a scalar that f is. Okay, so then what I'm going to do is I'm going to write my starting mixer model. And for my mixer, again, I'm going to have an inlet and an outlet port that are inputs for the inlet and output for the output. The mass is going to use my port, and then the difference is I'm going to define the inlet as a multi-port, which means that I'm going to be able to have more than one connection to that port. I'm then going to say my outlet flow rate is equal to the sum of the inlet flow rates, and the mass fraction out is equal to the sum of the mass flows in times the mass fractions in, and I'm going to do that for each element of the component list. So I'm going to do that for each Z where I is a member of component list, and then this sigma is implicitly then going to work over the connection set connection. So I'm going to have n connections summed over m variable mass fractions, and I'm going to divide that whole thing by the inlet mass flow, or which is equal to the outlet mass flow. So this should give me my mass fraction. Okay, so let's start off with that. I'll drag a mixer onto the flow sheet and I'll call it mixer. You'll notice that I'm choosing to name my blocks and streams. That's a preference of mine. If you come to settings, auto name, you can choose to check or uncheck the streams. I'll leave the streams checked just for this demonstration purpose. I'll then pick up my stream and I'll bring that stream into the mixer, and you'll see that works okay, but I'm underspecified by 4 variables. Why am I under by 4? If I look at the stream, I've got to specify my flow rate and my mass fractions, which is a bit fiddly and a bit of a pain in the neck. But once I've done that, I can hit run and the model converges, so that's good. The second, so this setting the mass fractions was a bit of a pain in the neck. So what I'll do is I'll cheat. So this is my my starting stream. I'm going to cheat and I'm going to add some code to it, where what I'll do is I'll use some of the logic. So I know I've got a property called isConnected for that inlet port in main. And if that's true, then I know that I do have a connection on the inlet. And then if it's not true, in other words, if it's false, then I know I don't have an inlet connection on that stream. And in that case, what I want to do is I want to have my flow rate and mass fraction fixed by default. So you can see I've just added this phrase to the old model. And now if I use one of these stream ones to come into my mixer, now it's specified correctly, and I've got that stream 1 set up, and you can see by default the mass flows and mass fractions are fixed, and they're blue showing you that that's the Aspen default. Just to sort of demonstrate that point, if I bring another stream in and connect it to the outlet port, you'll see I am still well connected, and now S3, that mass fraction is free. If I if I reconnect this port such that it's dangling, you'll see now they automatically switch to fixed. So that's using the structural if to do some clever things with ACM and just make it slightly easier for me when I'm working. Okay, so I've got a model set up. I've got those flows running through. But the sharp-eyed among you will notice that although I've got it set up, my mass fractions are each 0.5. It's just using the default value of 0.5. So while the maths is solving and it's acceptable, the physical reality isn't being matched. I really want Z, the sum of the mass fractions, to sum to 1. So what I can do is I can come again. So let's open up my old stream code. What I can do is I can come in and I can add some code to that stream. Again, now I'm using another one of the properties of the model. In this case, I'm using the size of the component list. And what I'm going to do is I'm going to set the value of Z, the mass fraction, to 1 over the size of the component list. So that then, if I've got 2 components, it'll be 0.5 each. If it's 3, it's a third. If it's 4, it's a quarter, 0.25. So that's then going to help me set my starting point with a mass fraction that sums to 1, and that's then going to hopefully make my overall model a little bit better. So let's do that. Let's get rid of those 2 streams and bring in some S2s. So I'll have some streams coming in. And now what you'll see is if I look at those streams, they're 1/3 because I've got 3 components. So my mass fraction is summing to 1, and now my overall model is more realistic in terms of what's going on. One last thing while I'm on that theme is setting it to the size of the component list is a reasonable option, but I may want to do it differently. So again, let me open up S2 so we can compare. If I look at S3 that I'm going to compare to, what I've done here is I've added 2 different elements. First off, I've created a component list called key, or at least I'm referencing a component list. In my model, I'm calling it key, and in the overall system, I'm calling it key. So I've had to come over to component lists and create another component set called key. So my default, I defined it's got A, B, and C in it. So that's what's picked up by default by component list. I've then created key, which has got just A in it. And so if I use this new component set to define a single component that's going to be the most prevalent component in my flow sheet, water in an aqueous system, for example, I can then use that to do some tricks and make the model behave in a more reasonable manner for me. So I've defined that component list key, and then the other thing I've done is I've defined an optional parameter, a logical parameter that I as a user am going to be able to use, and I'm going to determine whether or not to use that key. So I'm declaring that as a logical parameter, so it's got a true false by default. I'm going to make it false by default so that I keep my same structure as stream 2 by default. But now what I'm going to do is I'm going to say if I'm going to use that key, then for the element of the array in main.z referenced by that single variable, that single component in the component list key, set that mass fraction to 1. So in this case, it would be if key is water, then set my stream water mass fraction to 1, and then set my mass fraction for everything else equal to 0. So here I'm using some set maths where component list is one string array, key is another string array that just happens to have one element. And so I'm saying for everything that is in component list and not in key, then set that mass fraction to 0. So now if I flip the logic use key, I either set it all to component A or I set it to a uniform stream. So that's another little trick that's useful. So let's just demonstrate that quickly. If I drag this stream 3 in, now you can see I've got use key is false. If I choose to set that to true, my mass fractions go from being 1/3, 1/3, 1/3 to being all A. And obviously if I set it back again, it goes to 1/3, 1/3, 1/3. You'll notice that I use reset to default. That's just me being used to using ACM. it doesn't really make much difference, but there's often times where I use something like this use key and I embed that in some inheritance and it then overwrites as the inherited models do things. So I prefer to leave things at their default whenever possible, if that makes good sense. Okay, so let's use key in this case just for the fun of it. And so now I've got 3 streams entering that mixer. So that's all looking good. Okay, so that's various tricks and tips using structural and user-defined logic, and that's helping me set up the stream the way I'd like it to be set up. Let's go back to having just a single feed to this. Actually, let's use my best stream. So I'm going to go back to using just a single stream coming into this mixer, and I'm going to run it. So the model works, it's all looking good. If I have a look at the output, it's 1,000 kilos of A coming out of the system, as I would expect. What happens though if for some reason ACM gets this flow to be 0? What you'll see is my error messages get cross with me. It says, look, you're dividing by 0, that's not good. The equation you're dividing by 0 in is this one. I should have said earlier that in order to get all this higher level of debug information, I've right-clicked on the messages window, solver reporting level, and I've chosen to set it to high. Medium is the default when you first open ACM. But when I'm debugging, I tend to like to use high because it gives me a little bit more information. So it's telling me this is what's going wrong, and it's telling me why it's dividing by 0, and all that sort of good stuff. So that's not great. So let's try and avoid that divide by 0 error. So if you remember my mixer, I'd started off with dividing by as one of the options, and that's never a great choice. I always try and avoid dividing in ACM if I possibly can. Fortunately, ACM is set up so that it interprets the maths on the fly. You don't have to have a single variable on the left equals something on the right like you would in Python or Java or Fortran or whatever. What you can do is you can actually rewrite that equation. If I multiply both sides by the outlet flow rate, I can reset the equation like this. And so now, if I set that outlet flow rate, so let's quickly run through. I'll give myself that stream again coming in, and I'm going to set that flow rate to 0. You'll see now, and just so that this one solves, I'll set that back to 1. So now what will happen, what should happen, is it goes through and it says, I've solved, but now mixer 1 has indeterminate variables for outmain.z, a, b, and c, and it's reminding me down here. So what will happen is this will be embedded in the comments where it actually happens, and then ACM helpfully, before it finally declares itself finished, repeats that information at the bottom, so that if you have a large model, you can see where your indeterminacies are. And that helps find and debug the model. So why is it indeterminate? Let's have a quick look at that mixer 2 model. Well, I'm not dividing by 0 anymore, but if inlet flow is equal to 0 and outlet flows, then outlet flow is equal to 0. So I've got a 0 times something equals 0 times something. So the equation on both sides is 0, and there's no way for it to determine what outmain.z actually is. There's a couple of ways to fix that, a more robust way and a less robust way. What I'm going to do, first off, let's just pull up that mixer 1 code. One way to fix it is to play with the structure again. So this is maybe cheating a little bit, but if what I do is I come over and I say, again, I'm going to use the structural information about the model. So if I know that there's only one connection, if the size of the connection set on the inlet is 1, then I can use a different set of equations. Then I can just say the outlet flow is equal to the inlet flow, and I don't have to do any maths to do that. And similarly, the outlet mass fraction is equal to the inlet mass fraction. And so again, even if this is 0, even if the flows are 0, my outlet mass fraction is explicitly defined. Otherwise, yeah, then I've got the same problem as I had before. So if I do that, then for this case where it's mixer 1, if I do mixer 2 instead, and I have a single stream coming in, Actually, let's use stream 3, sorry. Then let me show you one other thing first. I've added those. I'm going to delete them again. I'm going to run just to show you that there are 16 equations set up. So I've got mass flow and composition, so n+1, so 4 for the inlet stream, 4 for the mixer, and I've got 4 for the stream, 4 for the mixer, so I've got 16, 4 for each set, 16 overall explicit equations in the system. With this mixer 2, if I drag it in and give it a feed stream and hit run again, you'll see that interestingly I've only added four new equations. And why is that? That's because Aspen has been smart enough to, or ACM has been smart enough to use what they call equivalencing. So because if I look at mixer 2, sorry, I'm explicitly saying, I'm using this side of the equation, I'm saying explicitly in equals out. Because these are unity, because these are always equal to one another, it's saying I can actually create a higher level variable, and rather than having this equation in my equation set, I can just leave it out of my equation set and instead reference that pointer where they're both using the same value. What that does is it makes my overall model slightly smaller, and so there's some advantages when you get to very large models in writing it this way, because it gets rid of some of the complexity. The other thing it's done, you'll notice that if I set S9 to 0, the flow to 0, and I hit run, you'll see that it's not creating any indeterminacy. Now, because it's explicitly following through, the composition out is exactly equal to the composition in, and so I'm as opposed to in mixer 1, where because it's not sure what the outlet is, it's just leaving them at their defaults and not changing the value. I'm now getting a rigorous and correct answer for the overall system. So that's a good trick to use, is for something like a mixer, if I know I don't need to use the mixer, then just bypass the calculation and just set the inlet as equal to the outlet. Okay. That's all good, but that's useful only if I've got a single element coming into my mixer, and that's probably not going to be happening very often. Usually I'm going to have multiple streams coming into my mixer. So what I can do to slightly help is, again, use that key variable trick. So if I compare mixer 1 and mixer 2, what I've done here is I've referenced that key element again. So remember, key is the single variable that I know is always going to be in the highest concentration. And what I'm going to do now is rather than just using that equation for all variables, I'm going to do it for all components other than the key, and then I'm going to force the sum of out main.z to equal 1. So even if I've got zero flow coming into the system, and I've got multiple streams coming in, it will at least force the mass fractions to 1. So let's quickly demonstrate that. So if I've got mixer 3, let's give it 2 streams coming in. And I give both of them 0 flow rate, so I will have that same indeterminacy that I had before. You'll see that it has now created all those extra variables, because I've got I have the mixer equations and I have the 2 streams. So once again, I'm at that n+1, n+1, n+1. So I've added 12 new equations to the system. So I've gone from 20 to 32. And what it's telling me is that, hang on a second, both B and C are indeterminate. And so I've got a problem still, but at least A isn't indeterminate. And now what's interesting is if I have a look at at mixer 1, you'll see that all the mass fractions are 0.5. Mixer 3, I've still got that problem where they're indeterminate, but now at least they sum to 1. So I'm forcing it to at least be reasonable. I prefer it to be 0.33, but it's currently summing to 1. There are a couple of strategies I could use here. I'm not going to go into those right now with examples, but I will just mention that if I take a look at the code here, what I could do is I can add a small number to the flow coming in, so that, for example, instead of using the flow, I could use the flow plus 10 to the minus 6, and then use n times 10 to the minus 6 on the outlet, and that would mean that if all the streams coming in tend towards 0, then the outlet mass fraction will tend towards the average of the inlet mass fractions, regardless of what the flow rates are. But as soon as that flow rate gets reasonable, then the outlet will tend towards that value. That, however, is pretty much where I wanted to stop. The last thing I'll do is just mention the value of adding syntax and bits and pieces. So you'll notice that with Mixer 3, I'd actually already created the summary table, whereas Mixer 1, I'm just using the all variables table, and that starts getting a little confusing. With Mixer 3, I added a summary table so that I could choose the order in which variables are shown, and I can choose not to show all of the variables if I want. With Mixer 4, what I've done is it's the same as Mixer 3, but I've come in and I've added some commenting so that I can see where my ports are, where my equations are. I've also chosen to name my if statements. That's quite handy if stuff starts going wrong. This debug window down here will tell you the equation that's having trouble. If I've named the equation and if I've named the if, then it can start helping me sort of see exactly which equation it is. Otherwise, it'll be equation 3922 in the middle of my system. So I've gone through and I've done that for my block and for my stream. Again, what I tend to do is declare my variables, declare my ports, do any configuration changes that I want, and then have my equations at the end. You may choose a different scheme, but this is quite a nice way of working because it sort of follows the logic of how you define variables. Okay, that's where I'd like to leave it for today. Thank you very much for paying attention. If you like it, please feel free to leave a comment and any other feedback. Thank you very much. Goodbye.